So let's walk through how to actually do this bootstrap procedure. Okay, so going through the steps of the application exercise, the first is to set a seed. And so I'm going to do that with the set seed function. You can set it to whatever you want. I'm going to set it to 1. There we go. And then the second question, and actually I can just include these together, is to use the sample function to sample from the following vector with replacement. So we were sampling from 1, 2, 3, 4, 5 with replacement. So I'm going to sample from that vector, and I'm going to set replace equals true. Okay, and so when I do that, wow, it looks like we got a lot of 2s on this particular run. Let's run it with that seed. So when I do the set seed, 1, I end up with 2, 2, 3, 5, 2. Now, if I set a different seed, I would get a different answer. This time I got 5, 2, 1, 1, 2. When I knit this document, if I leave my seed the same, I get that same, the output, the 2, 2, 3, 5, 2 that I saw locally when I had the seed as 1. 2, 2, 3, 5, 2. So that's why it's nice to always set a seed, because you know that you'll get the same answer in your R chunk as you will when you knit your document. And for that reason, often when I'm doing a random process, I like to set my seed in the same chunk as the random process I'm doing. It's good practice to always set your seed as close to the random process that you're implementing as possible, so that you make sure that you're kind of, you're aware just as a coder of kind of what's going on there. All right, so the next question says to, let's call this bootstrap function, is to write a function to perform a bootstrap. So I'm going to write one by hand. Hopefully it'll come out something like what I showed you in the slides. I think it will. So I'm going to call this bootstrap. This is in particular, we're doing what's known as a residual bootstrap. We can call this resid bootstrap. And it's going to be a function. And this is going to be a function of y. It's going to be a function of my residuals. It's going to be a function of, let's see, what else goes into this? My model that I fit. So it's my model. It's also going to be a function of my data. Okay. And so my residuals here, my E star, is going to be sampling with replacement from my actual residuals. And so I'm going to take my residuals from my actual model and I'm going to replace them. And I'm going to get that E star. Okay. And now that I've got that, I'm going to have my Y star. And this is going to be equal to Y hat. So maybe I'll plug this in here. Y hat. Plus E star. So that's my Y star. And I'm actually going to save this to my data set. That's going to make it a little bit easier to going forward. So I'm creating this E star. I'm creating this Y star. And I'm going to update my model. So this is the model that I fit previously. And now it's going to be Y star. So this new Y star that I've just created. And then I'm going to leave my X's the same. I'm going to set my data equal to my data. And then the thing that I want to actually pull out of this bootstrap are my coefficients. And so I'm going to pull out the coefficients. This is going to be my new model. I'm going to pull out the coefficients of my new model. So this will work like this. It's good practice to just write return here, even though it would work if I didn't, just to sort of keep in mind that we're writing a function and the thing we're going to be returning is this vector of coefficients. Okay, so hopefully that's going to work. Well, we'll try it in just a second and see, and if not, we'll troubleshoot. Okay, so using the function that we just created, run a bootstrap on the following model. So my model is going to be a linear model of miles per gallon, predicting miles per gallon from weight, CYL, the data is equal to MT cars. That's my model. We can take a peek at that model. Oops, mod. here we go. We've got our intercept is 39.6, our slope is negative 3.1, and that's our beta 1 value, and our beta hat 2 is negative 1.508. So that's our model. The other pieces that I need are my y hat, and I also need my residuals. So I can pull out my residuals from this mod. Let's look at those. Okay, that pulls out the residuals for all of those. And I can also pull out my y hat. There's a function called fitted that you've used before. I believe you used it in the lab. Pull those out, so now I've got my y hat values as well. So I've got y hat, I've got e, I've got my model, got my data. Okay, let's try it. Let's run just one to see how this works. So I called this function resid bootstrap. Okay, I'm gonna plug in y hat, I'm gonna plug in e, I'm gonna plug in my mod. I called this model equals mod. I'm gonna call this mod here. So y hat equals y hat, e equals e, model equals mod, and data equals MT cars. All right, so when I ran this one time, I ended up with 40, negative 2.9, and negative 1.8. Let's run it again just to see what we get. Oh, we get a little slightly different answer, 38, negative 2.4, negative 1.7. And again, a slightly different answer. So instead of just running this over and over and over again, I'm going to save this output. I'm going to use that, let's call this boot out. I'm going to use that map function that we learned about from the per package. So because I'm only using one function from the per package, I can just do this per with the double dots here, the double colon, map df. I'm going to do from one, let's do, did I say how many bootstraps? No, so let's do 1,000. And we're going to do this on this bootstrap residual. Now, when I run this, it should work. We'll let this run for just a second. Looks like it did. Some people were getting some errors when they were running this, and that had to do with having it actually was an old version of the dplyr package. And so if you installed a new version of dplyr, it would work, which I think is a little bit confusing because if you notice that this is not using dplyr, it's using per. But per actually depends on dplyr in certain cases, and in particular the map_df function, because it's operating on a data frame, it depends on the dplyr package, which is why that error was coming up. So if you ran into this error that was basically saying that your input needed to have names, that was the cause of that error. And so it should work if you just do install that package as dplyr to get the most recent version. I put a little note about that in the application exercise, but just in case you hadn't seen it. Okay, so let's look at this boot out object. So we've got 3 columns, 1,000 rows, a column for the intercept, column for weight, and a column for CYL. Okay, so let's calculate a bootstrapped percentile confidence interval for the coefficient associated with weight. This is going to be a boot CI. So how do we do that? We're going to use we need to pull out the 95th or the 97.5th percentile on the top for our upper bound, and we need to pull out the 2.5th percentile for our lower bound. So let's pull that out. Let's do the lower bound first. So the lower bound is going to be, take the quantile of boot out. We're doing this for the weight. We want the 0.975. And this will pull out or actually we want the 0.25 for the lower bound. Let's take a look at that and see what it is. Negative 4.54. Looks good. And it turns out you actually can do this to get both the upper bound and the lower bound. And so I'm actually going to call these CIs instead. I'm going to wrap this in parentheses like this so we can see the output. Okay, so our bootstrapped confidence interval is negative 4.5 and negative 1.69. Now we're going to use the standard error method for the coefficient associated with weight. Okay, so the standard error method, let's see. So this is the CI percentile. And now we're going to do boot CI standard error. And so that's going to be equal to that's going to be equal to the mean of our output for weight. So this is going to be this is basically our estimate for beta hat 1. It's the average value from that output, negative 3.1. And if we look at our model, that is pretty darn close. That 3.185 versus 3.191 as our average value for weight here. So that's our mean. That's our estimate for beta hat 1. And the standard error, so instead of, I'm going to do this as lower bound and upper bound. So the lower bound here, or I guess I could do it here. We'll do it as in just one fell swoop. So we're gonna make a vector that includes the lower bound and the upper bound. Okay. Oops. Okay, so it's going to be, both of them are going to start with the mean. The lower bound and the upper bound are going to start with the mean. The lower bound is going to subtract something. The upper bound is going to add something. And we're going to add this t star times standard deviation of that estimate. And here we're going to, instead of subtracting that, we're going to add it. So what we're doing is the standard error method basically uses the confidence interval formula that we know, except instead of using an actual beta hat value and the actual standard error of the beta coefficient for weight, we're estimating the beta hat value using the mean from our bootstrapped output, and we're estimating the standard error for that by taking the standard deviation of our bootstrapped output. Okay, so we still need to put in a t star here. So what would that be? So if you remember from our confidence interval, t star, it's going to be from a t distribution. We want the 0.975 percentile because we're calculating 95% confidence intervals. And our degrees of freedom here is going to be the number of rows, the number of observations in the MT-CARS data set, minus p plus 1, which in this case we had two variables in our model. Plus 1 is 3, so it's going to be n row minus 3. So we can take a look at that. It should be 2.0, yep, 2.05. So that's what it's going to be the t star. And let's wrap this whole thing in parentheses so we get some output when I run it. All right, so we get negative 4.68 and negative 1.68. So there we go. And now finally, let's compare this to what we get from the confint function. So let's run the confint function on the model. Okay, so comparing all of them, we end up with our percentile interval is negative 4.5 to negative 1.69. Our standard error method is negative 4.68 to negative 1.68. So this, it has basically, it's a little bit, has a little bit of a lower bound and a little bit of a higher upper bound. And then here it's negative 4.73 to negative 1.64. So there they are. Those are all of our values for all of these. We can, if we'd like to, we could plot this like I did in the slides. And so I'm going to go ahead and do that. So let's plot this output just to be able to visualize it a little bit better. So I'm going to plot that boot out. I'm going to plot those weight values. I want to plot the weight values. I'm going to do a histogram. Oops, of course we need to call the ggplot2 package in order to do that plotting. So there we go, I'm using the ggplot2 package. Let's make sure we put the bins equals 30 here. Okay, and now I can add a horizontal, or rather a vertical line for each of these. And so I'm going to add a solid line for our observed confidence interval here. So the CISE, this is going to be a solid line. And let's make this, oops. Okay, so this is for our standard error method. And let's do the same, except we're going to do it for our percentile method. Let's make that one blue. Oops. So that's what that looks like. And then finally, let's look at our confidence interval method, our normal confidence interval method. So I'm going to do the conf int of the model, and I want to take the second row, and I want both of the columns here. And I'll leave this one black so that we can, oops, I don't want that. I want the second row of this. So from looking at this, it looks like the confidence interval as calculated using our normal method is the most conservative. It's on the outside here in black, with the next most conservative being in red. And so the closest to that black line is our standard error method, with the percentile confidence interval coming a little bit closer in from there. So there you have it. Those are our bootstrapped intervals. I think the bootstrap is kind of a nice way to sort of think about how this can work, especially if we didn't have a situation where we had a normal distribution where we could just rely on kind of normal theory to be able to calculate these confidence intervals. If we wanted to be able to just do it through resampling, it gives us some more flexibility. I'm going to go ahead and knit that, and we're done.